Hi, welcome to this online class. This is John Liu. We're going to learn mechanics of materials together. As an introduction, mechanics of materials is a branch of applied mechanics that deals with the behavior of solid bodies subjected to various types of loading. The principal objective of this class is to determine the stress, strains, and displacements in structures and their components due to the loading acting on them. Let's start from chapter 1. In this chapter, we're going to learn the concept of stress, and you're going to learn the normal stress and shear stress and determine the stress under given circumstances. Before we introducing any new concept, we need to review some of the knowledge we learned from statics, and we're going to review free body diagram, equations of equilibrium, and method of section. All of those will be used a lot in this class, so it is necessary to learn, to know. And alright, let's look at our first example from statics. So here we have a structure ABCD. So ABC, it's a rigid beam, and there's a pin support at A, and there's a uniform distributed load acting on the beam ABC. And DC, it's a rigid beam connected at C and D, and at point D there's a pin support. So here we need to determine the shear force, normal force, and the bending moment acting at B of the structure. So we need to have a plan for solving this problem. So the first thing we need to solve is the support reactions at point A and C. And after we find support reactions, we can apply method of section at point B. Step 1 of solving this problem is free body diagram. We have the beam A, B, C, and at point A, we have a pin support which gives us support reaction at X direction and Y direction. And at point C, we have two force members. Therefore, FC has the same direction with the beam CD. And on the top, don't forget, we have this uniform distributed load. And there's another way to draw this free body diagram. If you don't like the uniform distributed load on the top, you can draw this. You can either draw the free body diagram like this or like this. With the free body diagram, we can move to the next step, which is the equilibrium equations. So we should have three equations. The first equation, it's all the forces on X direction. We assume the positive direction points to the right, so the summation of all the forces on X direction equals the AX plus or minus the X component of FC, which equals FC times 8 over 10 equals 0. And with this equation, we can get AX equals FC times 8 over 10. Even we don't know the magnitude of FC, we just list this as it is and move on to the equilibrium equation on Y direction. So on Y direction, let's define the positive direction points to upward, and the summation of all the forces on Y direction equals AY minus P, and minus the Y component of FC, which is FC times 6 over 10 equals 0. With this equation, we get AY equals P plus FC times 6 over 10. And we have another equilibrium equation, which is the moment defines the positive direction, which is the counterclockwise, and all the summation of moment about point A equals negative at P times the length of AB, length AB, and minus FC. So inside of this moment equation, the first term, it's a moment caused by this concentrated load P. And if you think about point A, P will cause a clockwise movement about point A, which has a negative sign in front of it. And if we consider FC, the Fx component of FC will go through the point A, which means there's be no movement of the X component. But if you consider the Y component of FC, and it will cause a clockwise movement about point A, which is also negative. That's why we also have a negative sign in front of it. From the moment equation, we can find out FC equals 2666.7 Newton. So we find our first unknown FC. With FC, if you plug FC back into AX and AY, you can also find out Fx equals 2133.3 Newton, and AY equals 2000 Newton. At the end of second step, we already found all the support reactions at point A and point C. All right. The next step, step 3, with knowing all the support reactions, we can apply the method of section. Since we're looking for the forces and bending moment at point B, therefore we need cut and apply the method of section at point B. So first, you will get two free body diagrams, right? So when you cut at point B, if we take the left side, and we will have a free body diagram like this. We still have the pin support at point A, and at point B is fully exposed, so that we have the shear force acting down and normal force acting to the right, and also we have a bending moment which is counterclockwise. And this is for left side. You can also take the right side, but you only need one. Now we can list all the equations of equilibrium. First, all the forces on the x direction, positive direction, points to the left, to the right. All the x direction, define the positive direction and list all the forces on x direction, which we have ax and plus mb, which is the normal force, equals 0. And we find out mb equals negative ax, which is, and for the y direction, positive direction, point up, we have ay points up, and we have the VB points down, which is negative, and we also have this, the distributed load, and we know the length of AB, and we know the magnitude of this distributed load equals 50 Newton per meter, and therefore we have minus 50 times 50 Newton per meter times 4 meters equals 0. From this equation, we get our VB equals 1800 Newton. And we also have moment equation, positive direction and summation of the moment about point A, because we have the VB could cause moment about point A, so therefore it's negative VB times 4, which is the distance, and plus this MB, the bending moment, and minus this distributed load will also cause a moment about point A, and that would be 50 times 4, which is the magnitude of the total distributed load times the distance, which is 2. The reason the distance is 2 because if you simplify this distributed load into a concentrated load, it were acting at the midpoint of AB. Therefore, the distance from the midpoint to A is only 2 meters. This equation equals 0, and from here we can get our MB equals, we get MB equals 760 Newton meter. And so far at this step, we find the normal force, the shear force, and also the bending moment. Hopefully this will give you a review of free body diagram, equations of equilibrium, and method of section. The previous examples are very important for this class. Now we're going to introduce a new concept, which is a stress. So here's the question: what exactly is the strength of a structure? Here we introduce stress, which is a measurement of stress, which is a measurement of strength. For stress, we have two different types of stress. One is normal stress, another one is shear stress. And we define normal stress as sigma equals the normal force over the area. And we define shear stress as tau equals the shear force over area. It is also important to know what's the unit of the stress. So the basic unit from the definition, we have Newton per meter square, and this also equals to Pascal. And we also use KSI, which is kilopounds per inch square. And also we have PSI, which is pound per inch square. The convention between PSI and Pascal is 1 PSI equals 6.895 kilopascal. And for the pin support, we have two different types. And this one on the left is called single shear. In this case, the shear force equals to the applied force. And the one on the right is called double shear. In this case, actually the applied force equals 2 times the shear force. So when you solve problems, make sure the pin support is either single shear or double shear. It will lead to a different result. Alright, let's look at an example of shear stress and normal stress. So here we have a slab which is subjected to an axial loading of 500 Newton on the bottom and the top, and determine the average normal and shear stress acting along section AA. So the section AA has the 45 degrees angle. So in this case, we need to resolve the force, the 500 Newton force, into its normal direction and shear force direction. Then the second step will be apply the definition of shear stress and normal stress to find out. So the plan of solving this problem is to resolve the 500 force to normal force and shear force respect to the section AA with this 45 degrees angle, and then we can apply the definition of shear stress and normal stress. So step 1, we cut this slab from the section AA and draw the free body diagram. And we have this 500 force, and we resolve this force into x direction and y direction. We resolve this force to normal direction, which is called Fn, and shear direction, Fv. The angle between the normal force and this 500 Newton force should be 45 degrees, and between the normal force and shear force is 90 degrees here. Now step 2, let's find out what is Fn and what is Fv. So here, F normal force equals the 500 loading force times cosine 45 equals 250 square root 2 Newton. The shear force Fa equals F times sine 45 degree equals 250 square root 2 Newton. So this is a special case because the angle is 45 degree. Therefore, the normal force equals the shear force. So step 3 is to applying the definition to find out the sigma and tau. From the definition, our normal stress equals the normal force over the area, and our shear stress equals the shear force over the area. Here we already find the normal stress and shear stress from the previous step. Now we need to find out what is the area. So in this case, since we cut the slab open from the section AA, the area here is the area we're looking for. So the area A should equals the 0.3 times this side, which is 0.04. And we get 1.127 square meter. Therefore, we can find out our shear stress and normal stress. Here we get 2783.9 Newton per meter square. For the shear stress, we have this. So here is how we find the normal stress and shear stress.